I've spent 5 years helping schools and makerspaces set up environmental monitoring stations, and I keep seeing the same pattern. Students collect what looks like beautiful data, graphs that look totally legitimate, until someone checks and realizes the temperature readings are 3 degrees Celsius off, or the CO2 sensor drifted after 2 weeks. The calibration kids need for environmental sensors isn't some abstract lab ritual. It's literally the difference between publishing meaningful citizen science data and collecting expensive garbage. I'm Kazuki Tanaka, and I've helped hundreds of young researchers fix these exact problems.
You're listening to the STEM Lab podcast. Quick note up front, everything you're about to hear, the research, the data, the writing, that's all been done and verified by real people. The voice you're hearing, though, that's AI generated. Just want to be transparent about that from the start. If you've been listening for a while, genuinely appreciate you being here. And if you're new, welcome aboard. We release new episodes every Monday, Wednesday, and Friday, covering hands-on STEM topics, fabrication techniques, sensor projects, all that good stuff. Today we're talking about something that separates real citizen science data from junk: environmental sensor calibration. Let's jump in.
This checklist covers every calibration step I use when setting up sensor arrays with students, from pre-deployment verification all the way through field validation. Whether you're working with a basic environmental combo breakout board, check the link below to see the current price, or a complete weather station, these procedures will get your measurements into publishable territory. Now, before you touch calibration coefficients or reference standards, you need to verify your sensors aren't physically damaged or defective. I learned this the hard way when a student team spent 3 weeks troubleshooting calibration drift that turned out to be a cracked sensor package. Start with visual inspection under magnification. Use a jeweler's loupe or USB microscope to check sensor packages for hairline cracks, corrosion, or solder bridges. I've found manufacturing defects in roughly 1 in 50 budget environmental sensors, and they always manifest as weird calibration behavior rather than complete failure. Next, test your power supply stability. Measure actual voltage at the sensor's VCC pin under load, not just at the power supply. Many so-called calibration problems with boards like the Adafruit BME688, check the link below to see the current price, are actually brownouts caused by undersized USB cables or shared power rails dropping 0.3 volts when Wi-Fi radios transmit. Document your firmware version. Record the exact library version, sensor driver, and microcontroller firmware you're using before calibration. I've seen Arduino library updates change ADC reference voltages or averaging algorithms, invalidating weeks of baseline data. Verify connection integrity. Wiggle every connector and I2C or SPI line while watching serial output. Intermittent connections cause random offset errors that look exactly like calibration drift, but won't respond to any calibration procedure. Run a thermal cycling baseline. Put sensors through 5 heating and cooling cycles, room temperature to 40 degrees Celsius and back, to identify units with poor thermal compensation. Quality sensors return to within 0.2 degrees Celsius of baseline, while defective units wander by several degrees. Do cross-sensor comparison. If you're deploying multiple identical sensors, and you should be for any serious project, run them side by side for 24 hours before calibration. Outliers more than 5% different from the median are suspect and deserve extra scrutiny. This verification process takes about 2 hours per sensor array, but it eliminates 80% of the calibration failures I see in student projects. For students building progressive skills in how to collect and analyze environmental data with sensor kits, these verification habits separate hobbyist tinkering from research-grade methodology. Moving on to reference standards. Your calibration is only as good as your reference standards. Professional metrology labs spend millions on NIST traceable references, but student scientists can achieve surprising accuracy with careful preparation. For temperature reference, use a NIST traceable alcohol thermometer, not a digital thermometer, which itself needs calibration, as your primary standard. Or verify your reference thermometer against ice water at 0 degrees Celsius and boiling water at 100 degrees Celsius at sea level, adjusted for altitude. I keep 3 different reference thermometers, and they must agree within 0.3 degrees Celsius or I investigate. Create humidity reference chambers using saturated salt solution chambers with lab-grade salts. Sodium chloride gives 75.3% relative humidity at 25 degrees Celsius. Magnesium chloride gives 33.1%. The National Weather Service publishes tables of equilibrium humidity for various salt solutions, and these cost under $10, but provide plus or minus 2% relative humidity accuracy. For barometric pressure cross-reference, compare your pressure sensor readings against local airport METAR reports available from NOAA Aviation Weather, corrected to your exact elevation. This requires understanding the difference between station pressure and sea level pressure, which is excellent practice for atmospheric science skills. To get gas concentration standards and CO2 calibration, use fresh outdoor air at approximately 420 parts per million in 2026 as your low reference, and your own breath in a sealed container at 3,000 to 4,000 parts per million as a high reference. Or purchase certified calibration gas if you're doing serious air quality sensor work. Verify reference stability. Measure your reference standards 3 times, 30 minutes apart. If they vary more than the sensor's advertised precision, your reference setup has problems, usually thermal equilibrium or contamination issues. Document environmental conditions. Record the exact temperature, pressure, and humidity when you calibrate, because sensor response curves shift with environmental conditions. I've seen CO2 sensors show 15% reading errors when calibrated at one temperature and deployed at another. Synchronize your time. Use NTP synchronized timestamps for all calibration measurements so you can correlate readings with reference weather station data later. Sloppy timestamp management has ruined more student datasets than bad sensors. The difference between good enough and research-grade calibration usually comes down to reference standard quality. Students working on citizen science projects need to internalize that their data credibility rests entirely on these reference measurements. Let's talk about two-point calibration procedure. Most environmental sensors ship with factory calibration that's close enough for general use but not suitable for scientific work. Two-point calibration corrects offset and gain errors, the most common sensor inaccuracies. Start with low reference point measurement. Expose your sensor to the lower reference condition. That's ice water for temperature, outdoor air for CO2, 33% relative humidity salt chamber for humidity. Leave it for at least 30 minutes to reach thermal equilibrium, then record 50 to 100 consecutive readings and calculate the mean. Never calibrate from a single reading. Repeat with high reference point measurement at your upper reference. Boiling water, breath CO2, 75% relative humidity chamber. Maintain the same exposure time and averaging procedure. The key is consistency between low and high measurements. Calculate your offset. Your offset error is the difference between the sensor's mean reading at the low reference and the actual reference value. For example, if your thermistor reads 0.8 degrees Celsius in ice water, your offset is plus 0.8 degrees Celsius. Calculate gain. Gain error is high measured minus low measured divided by high actual minus low actual. Ideal gain is 1.00, but most uncalibrated sensors show gains between 0.95 and 1.05. Implement the correction equation. Apply the formula calibrated value equals raw reading minus offset divided by gain in your sensor code. This two-line correction typically reduces error from plus or minus 5% to under plus or minus 1% across the sensor's working range. Do a verification measurement. Test your corrected sensor at a third reference point, room temperature for thermal sensors, 420 parts per million outdoor air for CO2 that wasn't used for calibration. If the error is still large, you either have a nonlinear sensor or contaminated references. I run this exact procedure with middle school students in our makerspace, and they consistently achieve accuracy comparable to sensors costing 10 times more. This is where environmental sensor calibration for kids transitions from following instructions to genuine experimental methodology. For students following a STEM learning path, two-point calibration is the gateway skill to quantitative science. Now, calibration isn't a one-time event. Sensors drift due to aging, contamination, and environmental stress. Professional monitoring networks recalibrate monthly or quarterly depending on sensor type. Start with co-location testing. Deploy your calibrated sensor next to an established reference station, weather station, air quality monitor, university meteorology site, for 48 to 72 hours and log parallel data. Deviations larger than plus or minus 5% indicate calibration problems or site-specific contamination.
Do inter-sensor validation. If you're running multiple sensors, plot their readings on the same graph with confidence intervals. Sensors should track within their specified precision. If one diverges, it's drifting and needs recalibration. Use known event verification. When weather services report specific conditions, cold fronts, temperature inversions, high particulate days, verify your sensors captured those events correctly. Missed events or wrong magnitudes indicate calibration or placement problems. Calculate drift rate. Plot calibration offset over time by periodic reference checks, monthly for temperature and humidity, weekly for gas sensors. If offset changes by more than 0.1% per week, investigate contamination or sensor degradation. Inspect for contamination. Do monthly visual checks for dust, spider webs, water intrusion, or corrosion. I've seen perfectly calibrated sensors fail because a spider built a web across the air intake, creating a 15% humidity error. Set reference comparison frequency. I use calendar reminders for recalibration, 2-week intervals for CO2 and VOC sensors, 1 month for particulate sensors, 3 months for temperature, humidity, and pressure. Different sensor technologies have different drift characteristics. Implement outlier detection algorithms. Use simple statistical filters in your data pipeline. Flag readings more than 3 standard deviations from the rolling mean. Sudden jumps usually indicate hardware problems rather than real environmental changes. This is where environmental monitoring transitions from a weekend project to serious science. Students using environmental monitoring kits need to understand that maintenance and validation are core experimental skills, not afterthoughts. The best calibration in the world is worthless if you can't prove it later. Research-grade documentation means other scientists can evaluate your methodology and reproduce your results. Keep a calibration logbook. Maintain a physical notebook, not just digital files, recording every calibration session, date, time, reference standard used, environmental conditions, raw readings, calculated corrections, and any anomalies observed during the process. Do pre-calibration and post-calibration comparison. Save raw sensor output files from before and after calibration so you can quantify the improvement. I require students to generate before and after accuracy plots showing error reduction. Track sensor serial numbers. Photograph or record serial numbers for every sensor and reference instrument. When you're running long-term monitoring with multiple sensors, mixing up which calibration belongs to which unit destroys data integrity.
Log environmental conditions. Record ambient temperature, humidity, and pressure during calibration, even if you're not calibrating those parameters. Sensor cross-sensitivities mean your CO2 calibration may be invalid if temperature changed 10 degrees Celsius between low and high reference measurements. Version your code. Use Git or at minimum time-stamped file backups to track every change to sensor reading, calibration coefficient, or data processing code. I've seen student teams accidentally revert to old calibration constants and invalidate weeks of data. Comply with metadata standards. Format your data files and metadata according to existing standards: NetCDF for atmospheric data, Darwin Core for biological observations. This seems like overkill for student projects, but it's the skill that prepares young researchers for actual citizen science contributions. Document chain of custody. If you're collecting data for regulatory purposes or scientific publication, document who had access to sensors when, what changes were made, and what data processing occurred. The scientific method requires traceability. Professional scientists spend more time on documentation than measurement. For students building data literacy through citizen science, these habits distinguish science from "we collected some numbers." Different sensor technologies have unique calibration quirks. What works for a thermistor doesn't work for an NDIR CO2 sensor, and missing these details causes most student calibration failures. For thermistor linearization, if you're using thermistor-based temperature sensors like in many Arduino kits, you need Steinhart-Hart coefficient calibration, not just 2-point. The resistance-temperature relationship is exponential, not linear, and simple offset gain correction leaves 2 to 3 degrees Celsius errors at temperature extremes. NDIR CO2 sensors have baseline drift issues. Sensors like the SCD41 Sensirion CO2 sensor, check the link below to see the current price, require ABC, automatic baseline calibration, where the sensor assumes the lowest reading in a 7-day period is outdoor air at 420 parts per million. Disable ABC if you're measuring in constantly high CO2 environments, or it'll self-calibrate to completely wrong values. Electrochemical sensors need conditioning. Gas sensors using electrochemical cells need 24 to 48 hours of powered operation before calibration to allow electrolyte equilibrium. Calibrating immediately after power-up gives you garbage coefficients that'll be wrong by 20% once the sensor stabilizes. Particulate sensors need cleaning cycles. Optical PM2.5 and PM10 sensors accumulate dust on the laser and photodetector, causing sensitivity loss. Some units, like the Plant Tower PMS5003, have automatic cleaning cycles that must complete before calibration, or your baseline will shift within days. Humidity sensors show hysteresis. Capacitive humidity sensors show different readings approaching a humidity level from above versus below. Proper calibration requires cycling through your reference humidity several times and averaging both ascending and descending measurements. Pressure sensors need temperature compensation. Absolute pressure sensors are highly temperature sensitive. Most include on-chip temperature compensation, but if you're reading raw ADC values, you need the manufacturer's temperature compensation formula, or your pressure readings will drift 2 to 3 hectopascals for every 10 degrees Celsius temperature change. I've probably debugged 200-plus sensor calibration issues, and 80% trace back to ignoring sensor-specific requirements buried in datasheets. Students transitioning from simple robotics kits to environmental monitoring need to level up their datasheet reading skills. This is where engineering meets science. Quick verification before deployment. Make sure sensors pass visual inspection with no visible damage, corrosion, or contamination. Reference standards should be validated against known physical points or cross-compared between multiple references. 2-point calibration should be completed with documented offset and gain corrections implemented in code. Calibration accuracy needs verification at a third reference point not used for the calibration procedure. All calibration data should be logged in a permanent notebook with timestamps, sensor IDs, and environmental conditions. You need a field validation plan established with co-location testing or periodic reference checks scheduled. Your drift monitoring system should be active with statistical outlier detection and regular recalibration reminders. Hardware-specific requirements need to be addressed for each sensor type in your array. Data formats and metadata should comply with standard schemas for your measurement type, and your code repository should be backed up with version control tracking all calibration coefficient changes. Let me address some common questions. How often do environmental sensors need recalibration for student projects? Temperature and humidity sensors need recalibration every 3 to 6 months if you're doing publishable work, while gas sensors, CO2, VOC, particulates, drift faster and need monthly checks. I set up calendar reminders for students to run their sensors against reference conditions, and if offset has changed by more than 10% of the sensor's precision spec, we run full 2-point recalibration. The recalibration frequency also depends on environmental stress. Sensors in outdoor weatherproof enclosures need more frequent attention than ones in climate-controlled indoor environments.
Can you calibrate environmental sensors without expensive reference equipment? Yes, with careful technique, you can achieve research-grade calibration using ice water at 0 Celsius, boiling water at 100 Celsius, adjusted for altitude, saturated salt solutions for validated humidity points, outdoor air at 420 parts per million CO2, and NOAA weather station data for pressure reference. I regularly help students achieve plus or minus 1% calibration accuracy, spending under $20 on lab-grade salts and a quality alcohol reference thermometer. The key is meticulous documentation and statistical averaging of many measurements rather than relying on expensive instruments. What's the difference between factory calibration and field calibration for student sensors? Factory calibration is performed under ideal lab conditions at specific temperature and humidity using NIST traceable references, giving you accuracy typically around plus or minus 3 to 5% across the sensor's full range. Field calibration corrects for the specific environmental conditions and measurement range you'll actually use. I've seen factory-calibrated sensors show 10 to 15% errors in field conditions because temperature, humidity, or pressure differs significantly from calibration environment. For starting citizen science projects, field calibration against local references is more important than factory specs. The calibration habits you build now scale directly to professional practice. Every environmental monitoring network, from NOAA weather stations to EPA air quality systems, follows these same principles: validated references, documented procedures, drift monitoring, and periodic recalibration. I've watched students who mastered environmental sensor calibration procedures go on to publish data in actual scientific journals and contribute to regional environmental monitoring networks. The difference between sensor tinkering and citizen science isn't the hardware, it's the methodology. When you can document your calibration chain, quantify your measurement uncertainty, and demonstrate validation against established references, your $35 sensor array produces data as credible as equipment costing thousands. That's not an exaggeration. I've seen it happen in our makerspace dozens of times. Your calibration logbook is your scientific credibility. Keep it detailed, keep it honest, and keep it current. That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes drop every Monday, Wednesday, and Friday, so there's always something coming down the pipeline. If you got something out of this one, it'd mean a lot if you could leave a 5-star rating and write a quick review. It's honestly one of the biggest ways other people find the show, and it helps us keep doing this. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. Appreciate you being here.